Hi, in this video, I'm going to go through the OCR A-level chemistry paper. This is paper 1, and it's the 2021 paper. I'll just do the first half in this video and the second half in a later one. Okay, so let's start with multiple choice. Okay, which statement describes electronegativity? Okay, well, electronegativity is the ability of an atom to attract electrons towards itself in a covalent bond, right? So the right answer there is C. A is just obviously wrong. B, well, it's not to become a negative ion. We're talking about covalent compounds. Electronegativity is when you're talking about covalent compounds and covalent bonds. Right, the chlorate 7 ion has a 1- charge. What's the formula for sodium chlorate 7 then? Right, okay, so sodium is always a 1+ ion. So that means the chlorate ion has got to have a charge of -1. And let's use this little formula. So sum of the oxidation numbers is going to be equal to the charge on the species. Well, the ion that we're talking about, the chlorate 7 ion, this must have a charge of -1. Okay, so that's equal to -1. We know the oxidation number of chlorine in there is 7, so +7 for the chlorine. And we don't know how many oxygens we've got there. Well, each oxygen has got an oxidation number of -2. And we have got, let's say we've got X oxygens, okay? So we end up with that equation, +7 - 2x is equal to 1. So we get -2x is equal to -8. So that means X is equal to 4. So we've got 4 oxygens. So it is that one is the answer. You should probably know anyway that this ClO3-, that's the chlorate 5 ion. These two compounds don't exist. There's way too many oxygens in them. So the answer is B to that one. 2 is B. Right. Balancing an equation now. So you can try this by trial and error. But if you look at this, this is a redox reaction. So let's do it with redox numbers. Now let's look at the silver. The silver is going from Ag to Ag+. That's going to lose it. That's losing 1 electron. Let's look at the nitrogen, okay? Because that changes. That's nitrogen. The nitrate ion is a +5 oxidation state, and here it's got a +2 oxidation state. So if we go from +5 to +2, that means it's gaining 3 electrons. So that means we're going to need, because the silver is only losing 1, we need 3 silvers for each nitrate. So the balancing number there is going to be a 3, 1 in front of the nitrate. We're going to have to put a 3 there. And how many, right, so we've got, on the left, we've got 6 oxygens. We've only got 2 oxygens on the right. So we're going to have to put a, 2 in front of the H2O. And that means that we have to balance with the hydrogens. We need 4 hydrogens. So that is, and 1 nitrate ion and 1 NO gas. Which numbers for Ag and H2O balance the equation? So we want 3. And so that one is, this is the correct, it's D. Okay, which sample contains the greatest number of molecules? So what we're going to have to do here is obviously we're going to have to find out the number of moles. Moles equal to mass over mR. So A, well, the mR of that, you can ethine quickly work that out. It's going to be 26. So that's going to be 140 over 26. B, that's 30 is the mR of ethane. So that's 180 over 30. C, C4H10, that's 58 butane. So it's 240 over 58. And D, that's benzene. That's got an MR of 78. Okay, so that's going to be 400 over 78. Okay, So quickly we can see there, this is a nice easy number to work out. 180 over, that's exactly 6 moles, isn't it? Okay, so we've got 6 moles of that one. Now, I think you can see A, 140, that's going to be less than 6 moles. Okay, so that's not as much. So it hasn't got as many molecules. It's less than 6, about 5. Right? You can do it on your calculator. We just do it in your head. C, 240 over 58, that's about 4, so that's way less, so it's not that one. And D, 400 over 78, that's about 5. So this one is the most. Okay. B is the answer there. Okay, so a reacting mass calculation here. So chromium 3 oxide is reduced by heating magnesium. Okay, so we now have to write an equation for that. So let's write that down. So it's going to be Cr2O3. Magnesium is going to reduce it. Magnesium is obviously going to form magnesium oxide. We should know the formula of that is MgO. Mg is a 2+ ion, oxygen is a 2- ion. And we're going to get 2 chromiums there. We need to balance that. So we're going to need 3 magnesiums there to balance that equation. So the important thing to notice there is that 1 mole of that is going to need 3 moles of Mg. That's the ratio. So now we need to work out how many moles of this we've got. So moles of chromium 3 oxide is equal to mass over Mr. We've got a mass of 11.4. The Mr of this stuff, or chromium, is 52. So the Mr of that works out to be 152. Okay, so that gives us 0.075 moles of the oxide. So how many moles of magnesium are we going to need? We're going to need, well, it's a 1:3 ratio. We're going to need 3 times that much. So moles magnesium, 0.075 times by 3, which gives us 0.225. Now we need to work out the mass of magnesium. That's the moles multiplied by the AR of magnesium, atomic mass. So that's 0.225 multiplied by the AR of magnesium is 24.3, and that gives us 5.46 grams. So choosing the right option there, 5.D, fuck that one there. Okay, so this one, not making a solution. Okay, so you've got 100 centimeter cubed of magnesium iodide. As the concentration is that. Okay. The student plans to dilute the iodide concentration, not the magnesium iodide, the iodide concentration. So what we need to do here is we need to work out our mole. What is the concentration of this solution? So with respect to the iodide ion, well, 1 mole of magnesium iodide contains 2 moles of iodide atoms, so it's equal to 2 times 0.4 is 0.8 mole per decimeter cubed. So that's one possible. If you forget to do that, you'll get the wrong answer. So the final concentration, so the concentration of iodide ions in the original solution is 0.8. So let's work out how many moles of iodine we've got there. Moles of iodide in original. Concentration times volume. That's 0.8. And the volume is 100 centimeters cubed, which is 0.1 dm cubed, equal to 0.08 moles. Now, the final concentration we want is 0.25 moles per decimeter cubed. Okay, so with concentration, moles over volume, we know the moles of iodide, we know the concentration, 0.25. We want to work out what volume we need to put that into, total volume. So the volume is going to be equal to moles over the concentration. The moles we've got is that, 0.08. The concentration is 0.25. That gives us a value of 0.32 dm cubed. That's the volume. That's equal to 320 centimeters cubed. I have to be a little bit careful there. D is not the answer, because what volume does the student need to add? Right, the total volume should be 320, but we've already got 100. It's already 100. So how much extra water? Well, it's 320 minus 100, which is equal to 220. Okay, so C is the correct answer there. Right. Which row shows elements in order of increasing first ionization energy? Now, there's a whole mishmash of different elements there. But what I would suggest, the way I do, the quickest way I think, is to look, as you go down any group in the periodic table, and you stick to the same group, we've got noble gases there, all right? The ionization energy decreases as you get more shielding, okay? The ionization energy decreases. Now look, we want to put them in order of increasing ionization, okay? So that means we must be going up. If there's two elements in the same group, we must be going up the group. Well, let's look at A. Which elements we've got in the same group? We've got phosphorus and nitrogen. Look, there they are. Phosphorus and nitrogen. So we should be going up the group. Phosphorus and nitrogen, we are going up the group, so that's a possibility. That might be right. Let's look at B. Now B can't be right because look, nitrogen and phosphorus here, they're in the wrong way around. Okay, phosphorus has got a lower ionization G than nitrogen, so it can't be that. Likewise, C can't be right for the same reason. And here I can't use that approach for D, but what I can do is I can look at carbon and silicon are both in the same group, group 4. And again, we're going down the group there, carbon to silicon. Look, silicon is below carbon, so it can't be that one. So the only one it can possibly be is A. So that is our answer there. But there are other ways of doing that, but that's the way I'd probably do it quickly. Right, bond enthalpy calculation then. Okay, so we've got to work out the enthalpy change for this reaction here, the oxidation of hydrogen sulfide to give sulfur dioxide and H2O. So I like to do these by drawing a Hesse Law diagram like that. So I've drawn out the molecules, show the bonds, avoids confusion. Right, so on the left, we've got the hydrogen sulfide and the oxygen. Okay, we're going to, on the red arrow, we're going to break all of those bonds, okay, which is, of course, endothermic. So that's going to be positive signs. Well, what bonds are we breaking there? We're breaking we're breaking 4 of the HS bonds, and they are each a value of 346. And we're breaking 3 oxygen-oxygen double bonds, and they have a value of 498. Let's add all that lot up together. You get 2,878, and that's going to be a positive number. We're breaking the bonds endothermic. Now, we've broken on this green arrow, we're building all the atoms, gaseous atoms, back up into new molecules. So what are we forming here? We're forming 4 of these sulfur oxygen double bonds, and they have a value of 531. And we're also forming 4 hydrogen oxygen bonds there, and they have a value of 464. Add all that lot up together, you get 3980. And importantly, because we are making the bonds, this is going to be exothermic. So we put a negative sign in there. Now to work out delta H for the reaction, all we have to do is write Hesse's law. So delta H, right, we're following that red arrow. So keep the sign is 2878 going down. And then we are going back up on the green arrow. So keep the sign there, that's 3980. Put that into the calculator, we get a value of minus 1102 kilojoules, which is B. Up there is our answer to that question. Right, this is a bit of an unusual question, this one. Okay, so we've got the system at equilibrium, and we've got to find out which one would have the highest carbon monoxide at equilibrium. Well, let's look at A. We start off with carbon monoxide, 1 mole of carbon monoxide, and NO2. So some of it's going to react. You can get some products. So how much CO have we got left at equilibrium? We've got less than 1 mole. Okay, so it's got to react. Okay, now let's look at B. Now we've got all the reactants. We've got carbon monoxide, and we've got some products. So that when it goes to equilibrium, that's going to go slightly backwards. Okay, to make some NO. There isn't any NO2. So that means the amount of CO is going to go up. We started off with 1, so we're going to have greater than 1 mole of CO there. That one. In C, let's see what's happening there. We start off with 1 mole of CO. We haven't got any NO. So that reaction is going to go forwards a little bit to go to equilibrium to make some NO. So we're going to have less than 1 mole of CO. So at the moment, it looks like B is the right answer. Let's see what happens with D. Right, D, we haven't got any CO. So the equilibrium is going to go backwards, but and so we're going to have more than 0, but it can't be. We can't have as much as 1, because you need, if you did have 1 mole of carbon monoxide, we'd have to use up all the carbon dioxide, and that's not going to happen because we've got to have some products. So that's going to be less than 1 mole of CO as well. So our only possible answer there is B. I can't remember seeing a question like that before. It's quite interesting. Right, this question is a fairly standard. Work out the pH of a weak acid when you know the concentration, and they give you the value of Ka. So working out the pH of a weak acid. So how do we do that? Well, we probably do it more quickly than this, but I will just say, right, so we've got a weak acid, we've got HA. And it's going to, we put into water, some of it's going to dissociate like that. So I'm going to put down start concentration there. And I'm going to write equilibrium concentration there. Now the start concentration, I mean, is when we put in the HA and that first instant when none of it has had a chance to dissociate. So that's going to be 0.5. We're going to say A minus is obviously going to be 0. H plus, we're going to say 0. It's not really 0 because the water's got a tiny bit of H plus in it. That's negligible, so we can ignore that. Now let's say equilibrium concentration, X of it dissociates. So the conc of HA has gone down by X. 1 mole of HA gives you 1 mole of A minus. So that means the concentration of A minus is X, and also the concentration of H plus is X. We write down our equilibrium expression here. Ka is equal to H plus A minus over HA. Let's put our numbers in there. So Ka is going to be, we have H plus concentration and A minus of both X. So that's going to be X squared. And what's the concentration of HA? It's 0.5 minus X. And this is where we do the usual little cheat. Because HA is a weak acid, it's a very weak acid, it's a weak acid, that means that X is tiny compared to the 0.5. So 0.5 minus X is approximately equal to, X is really small, is approximately equal to 0.5. That's what we always do. So that means we can get rid of that. That means we're not going to have a quadratic equation to solve, much easier. So X, don't forget, is equal to H plus concentration. So I'm just going to put that in there. So Ka is equal to the H plus concentration over 0.5. They don't give us Ka, but they give us pKa. pKa, they tell us, is 4.76, okay? Scroll up a bit. Oops. Okay, pKa, 4.76. So that means Ka is equal to 10 to the power of minus 4.76. Happy with that? Right, let's put on, let's rearrange that first of all and then put the numbers in. Okay, let's rearrange that so we get H plus squared is equal to Ka, which is 10 to the power of minus 4.6, multiplied by 0.5. Now let's evaluate that on the calculator. We get 8.68 times 10 to the minus 6. Take the square root of that to get H plus concentration. Square root of that is 2.94 times 10 to the minus 3. That's the, and to work out the pH, we take the minus log of that. And do that, we get pH minus log of 2.94 times 10 to the minus 3 is 2.53, which is, I think, is option A. Okay, now this one here, the feasibility of a chemical reaction depends on delta H and delta S, okay? Which row has the signs for the reaction that's feasible at high temperatures and not low temperatures? Again, this is a very common question. We need to have a think about delta G here. So what's the expression for delta G? Delta G is equal to delta H minus T, the absolute temperature, delta S, okay? So we're going to linearize that. So this is where I would think about these. So linearize that. Y is equal to the equation for a straight line. Y is equal to mx plus c. So if we're going to plot a graph like I was shown at the bottom there, we're going to plot a graph of how delta G, bottom there, how delta G varies with the absolute temperature. There's T. Okay, right, we do that. So delta G is going to be our Y. Delta H means it's going to be the intercept on the x-axis. That's there. X is obviously the absolute temperature T. So you can see there that the gradient M is equal to minus delta S. Okay. So let's have a look at those. So that's the four ways those lines could go, isn't it? Right, right, so let's just have the four ways those lines could go. Now, don't forget our intercept. So let's look at the first one here. Now, this first one is never going to be feasible, is it? Because look, we know that delta G, for a reaction to happen, delta G must be negative, must be greater than or equal to, sorry, less than or equal to 0. Delta G is going to be negative. And look in this first graph here, number 1, delta G is always positive. So that reaction would never happen. It's impossible. Let's just see what kind of reaction that is. Well, look, we can see there we've got delta H is positive because the intercept is positive, yeah? And the gradient is positive. It's going up like that. So that means delta S is negative. Okay, so that one is not possible. Just okay. Let's look at the one that we want. It's feasible at high temperatures. So which graph do we want? Feasible at high temperatures, but not low temperatures. Well, it's this one we want here, isn't it? Yeah. Because look at low temperatures, the delta G value is positive there. You get past this critical temperature there, and delta G becomes negative. So what can we say about that reaction? Well, we'll look at the intercept there. The intercept is positive. So delta H is positive. and look at the gradient of that line. Well, the gradient is negative. So that means delta S must be positive. So we want a positive delta H and a positive delta S. So A is our answer there. Alternatively, you can think about this logically. I'll just write down the expression for delta. If you're going to do a multiple choice question quickly, maybe you don't want to do that. But I always like to think of those problems like that using those graphs. But if I just put right down the equation delta G, okay, delta G is equal to delta H minus T delta S. Okay, well, we can see there, let's have a think about why it's A. Well, delta H is that's positive, and that's going to tend to make delta G positive. But at very high temperatures, if delta S is positive, that's positive there, all of this, that's all going to be negative. And that, for that to become a negative enough to cancel out that amount of positiveness, you've got to have a high value of T. Okay. Right, 2 redox systems shown there. All right. Which species in the 2 is the strongest oxidizing agent? Let's think about what side do we have the oxidizing agents. Now, oxidizing agents do what? They accept electrons. They take electrons off things and become reduced themselves. So which side on the left, is it the left or the right that's accepting electrons? Well, it's these two. Yeah, these are the oxidizing agents, aren't they? The Fe2 plus and the Cu2 plus. They're the oxidizing agent because they accept the electrons as the equation goes forwards. The metals themselves, Fe and Cu, well, they go backwards, they give away electrons. They're things which give away electrons, they're reducing agents. So we've got the oxidizing agents. Which one is the best one? Well, it's going to be the copper is the best one because it's the most positive one. The copper is the best oxidizing agent because it's the most positive. It's the best at attracting electrons towards itself. What charge will electrons have? They're negative. So the most positive electrode is going to be the best one at accepting electrodes. That means the most best at accepting electrons means it is the best oxidizing agent. So the answer there is the copper 2+ ion. Okay, this is the trending boiling points down the halogens group. So we've got to remember the halogens exist as diatomic molecules, okay, like that. All right, which is the bromine, as an example there. Now, when we boil halogens, are we breaking the covalent bond between them? This covalent bond, definitely not. All we're doing is we're breaking intermolecular forces, aren't we? And what kind of intermolecular forces have we got? Have we got a permanent dipole? Well, we haven't, because the electronegativity of bromine is the same as bromine, so there's no permanent dipole. Obviously, no hydrogen bonding. So the only kind of intermolecular forces we've got are going to be these temporary dipole, so London forces, yeah. Right, now they do get bigger as you go down the group, as you go down from fluorine, bromine, chlorine, iodine, because the molecules are getting bigger, there's more electrons, so the London forces are stronger. Okay, the trending boiling points, the induced dipole interactions, the induced becomes stronger. That explains it. The covalent, there's nothing to do with it. Okay, the permanent, there ain't permanent life, so that's wrong. So the only possible one it can be is D. Okay, this is a molecule of ClNO. Right, so we just have to remember group periodic table. We're going to draw a dot cross diagram. You can draw it very quickly in the exam. So group 7, group 5, and group 6. Right, let's do the chlorine. So we've got a single bond between the nitrogen and the chlorine. So we've got that. The chlorine has got 7 electrons. I've only drawn 1, so we need to draw 6 more. So there's 3 lone pairs in the chlorine there. All right, let's do the nitrogen. We've got a double bond here, so you've got 2 electrons from the nitrogen, 2 from the oxygen. Let's fill the oxygens in. So oxygen, the red dots, oxygen is in group 6. So we need to do 4 more, 2 lone pairs there. Nitrogen, finally, I've drawn 3 blue dots for nitrogen. It should have 5 electrons, so you need another lone pair there. Okay, so let's think about that. Is it a polar molecule? First of all, yes, it is, because all those elements have all got different electron negativities to each other, and it is not going to be symmetrical. Okay, so let's jump to that one. It won't have a bond angle of 180. Why not? We'll look at the nitrogen there. You haven't just got 2 bonding pairs, you've got 2 bonding pairs and 1 lone pair. So you're not going to get a 180 bond angle. It's going to be like trigonal planets. The bond angle will be about 120, but it'll be a bit smaller than 120 because the lone pair causes more repulsion. Yeah. And so 3 is wrong. And that also explains why the molecule is polar, because it's not, it's not symmetrical. Has it got 6 lone pairs of electrons? Well, you've got 1, 2, 3, 4, 5, 6. That's right. So 1 and 2 are correct. So B is the answer. Okay, so this ammonium iron sulfate is a hydrated double salt. Okay, so we need to find out what have we got in, what kind of iron have we got? Is it Fe2 plus or is it Fe3 plus? Need to think about that. Right, so if we can forget about the waters there, we know this charge on the sulfate, there's 2 sulfate ions, each of those got a -2, so you've got a -4 there. We know that ammonium ion has got a +1 charge. So that means the ion there must have a +3 charge, right? So all the charges add up to 0 in the ionic compound. So we've got an NH4 plus ion. We've got 1 Fe3 plus ion. And then on the negative side, we've got 2 lots of SO4, 2 minus, which makes 4 minus. Yeah. So that's the logic there. Right, so we now have to think about how does Fe3 plus, what happens when you add NaOH to Fe3 plus ions in solution? Do you get a green precipitate? No, you don't. You get a brown precipitate. You get that. That precipitate, which is brown. So that's wrong. Reacting with barium nitrate. Right, now that makes a white precipitate. Barium nitrate is a test for sulfate ions, and you get barium sulfate. So, and you've got sulfate ions there, we have. So yeah, 2 is correct. If we add NaOH, do we get a red-brown precipitate? Yes, we do. That's this stuff we're talking about there. And do we get an alkaline gas? Yeah, you do. Remember, if you get ammonium ions plus OH minus, OH minus is a much better base than ammonia. So you get NH3 and H2O, and NH3 is the alkaline gas they're talking about there. So that's right as well. So 2 and 3 are correct. So C is right there. Okay. Now I think that brings us to the end of the multiple choice section. So I'm just going to change the whiteboard and move on to the longer answers now. Okay, so that's the first question here. Question 16, okay. Now this is about, it's a fairly straightforward question. Magnesium has metallic bonding and is a good conductor of electricity. Describe with the aid of a label diagram the metallic bonding. Okay, include the charges on your particles, 3 marks for that. So let's draw the diagram and just what you'd say. This is, again, this is not really much past GCSE, but in metallic bonding, what you get the metal ions in a regular arrangement. So you need to draw some kind of irregular arrangement, make sure it's all It's not just random all over the place, okay? And they're ions, so you have to study the charges on them. Now it's magnesium, magnesium in group 2, so it's going to be a 2+ ion for each of those. I won't write it in all of them, but you probably should. Right, and then we have a sea of delocalized electrons, don't we? So these are all the delocalized electrons. They've got a negative charge in them. Put them around, okay. And so there's our diagram. Explain why it conducts electricity. Right, so this is described in metallic bonding. Well, it's the attraction of the positive ions for the negative delocalized electrons that's holding the whole thing together. Explain why it conducts electricity. Well, because you have delocalized electrons which can move. Okay, that would get you 3 marks there. Okay, so now on to ionization energies of magnesium, the successive ionization energies. Okay, so they're from 1 to 12 there. Write an equation to represent the 4th ionization of magnesium. So that's when it's losing its 4th electron. So it's already lost 3. So it's going to be an Mg, start off as an Mg3+ ion. And that's always in the gaseous state. That's the state symbol there. It's going to lose 1 more electron. It's going to form Mg4+. That's also going to be a gas and an electron. Don't really need the gas for the electron. Okay. Explain how the successive ionization energies provide evidence that magnesium is in group 2 of the periodic table. It's only 1 mark here, okay? So if it's in group 2 of the periodic table, it means it's got 2 electrons in the outer shell. So the first 2 electrons should be quite easy to remove, and then there should be a big jump to remove the 3rd one. And that's what we see here. So the first ionization energy is that it doubles roughly there, but then when you're from the 2nd to the 3rd, because you're entering a new quantum shell, it goes up by a factor of about 5 or something, doesn't it? You get a really big jump there. And then the jump between 3 and 4 is less big because it's in the same quantum shell. But I'd probably use the word quantum shell there. A minute. Sorry about that. Parcel delivery interrupting my video. Never mind. Okay, right. Right. So I would use the word quantum shell in your answer there. New quantum shell. Right. Right. This is electrons occupy orbitals. In table 6.2, tick below the ionizations that are responsible for removing an electron from a full orbital. Be a bit careful here. Okay, so I've written out the electronic structure of magnesium. So let's see so ionization number 1. Well, I'll write it here. So we're removing it from 3s. That's 3s2. So that's a full shell, and this one's coming. The atom's going to be 3s1. The ion is 3s1. That's going to be 2p6, 2p5. 2p4, p3, p2, p1, and then going into the 2s shell, so that's 2s2, that's 2s1, then going into the 1s shell, so that's 1s2 and 1s1. So, right, ionized numbers that are responsible for removing an electron from a full orbital. Okay, so it's obviously going to be that one because that's full. 3s is full there. 2s is full there, and 1s is full there. Now we have to be careful here with the p orbitals because of course there are 3 p orbitals. I'll draw them like that. So when we've got 6 electrons, so 2p6, are we removing it full for 1 year? We're removing it, say, from there. That's going to go. So that one will also be going from a full shell. Now when we do 2p5, you don't remove that electron, do you? okay, you remove, it's slightly easier to remove this one. Okay, so that one's going to go. So you're removing that from a full orbital there, from the full p orbital. So that one's full. And then we're removing this one here. That's the same again, isn't it? That's going to go from there. So that's from a full orbital. Now when we go to 3, that one goes, and that's not coming from a full orbital. So there's the green ticks in the right places. So they should be in 1, 3, 4, 5, 9, and 11. Okay. Important to remember that it's easy to forget and think, oh, the p orbital is just one orbital. It's not. It's 3 separate orbitals. Okay. Enthalpy change of solution, magnesium fluoride. Okay. So they've given us the lattice enthalpy and the hydration of the magnesium ions and the fluoride ions there. Okay. Explain what is meant by the enthalpy of solution. Well, the enthalpy of solution is the enthalpy change occurring when 1 mole of substance is dissolved in water. Okay. Now we need to have a look at this is an energy level diagram to work out what's going to help us to work out the enthalpy of solution. Okay, so on the dotted lines, fill in the species. Okay, so what we've got here, we've got magnesium, we've got in the gaseous ions, and they're forming the ionic solid there. So I'll just write, that's not part of the answer, that's the lattice enthalpy, that's going to be that change there, lattice enthalpy formation. Now down here, when we do these cycles, we always have the ions in aqueous solution. So I'm going to put Mg2 plus Aq and 2F minus in aqueous solution as well. We've got the, so that happens in 2 stages there. So this first arrow here, we are hydrating. Are we hydrating the Mg2 plus ion, or are we hydrating 2 fluoride ions? Well, that arrow is slightly smaller. So we need to have a quick look at the values there. And you see there, the value, the enthalpy of hydration of magnesium is really big because magnesium is a small ion, nearly minus 2000, where each fluoride is only about 500. So this small change here, drawn with the green arrow, that's when we're hydrating the fluoride ions. So the magnesium ions are going to still be gaseous there. And we've just hydrated the fluoride ions. Aqueous, rub that out there. And then in this next step here, in blue, yeah, we are hydrating the magnesium ions. Goes from magnesium gas to magnesium AQ there. So that's that bit there. Now it's going to ask us in the next bit of the question, it is going to calculate the enthalpy change, okay, of the solution of magnesium fluoride. So let's do that. But put the numbers in there. Okay, so lattice enthalpy, well, that's this number over here. That's so the lattice enthalpy is minus 2926. This blue one here, what we're doing there, we're hydrating 2 fluoride ions. So that's 2 times minus 506, so that's 1012, isn't it? And this red line here, we are hydrating just the magnesium ion, so that's minus 1920. Okay, and finally, we've got to work out, this is delta H sol here. Why is it delta H sol? Well, look, we're turning 1 mole of magnesium fluoride solid into the ionic, into the ions dissolved in water there. So that is delta H sol. So we've got to work out the value of that blue arrow. So what we've got to do if we just add up those two together, what do we get as a values there? We get, I'm not going to worry about the sign, I'll tell you why in a minute. You get 2932. Okay, so you can see that this blue delta H sol has got to be equal to this number minus this number. And that's equal to 6 kilojoules. But we need to think about the sign. Now look, that arrow is going down. That means it's exothermic. So it is minus 6 kilojoules per mole. That is our answer, the enthalpy of solution. Yeah, that diagram is fairly, that energy level diagram is a standard way of working out delta H solution. So you should know it. The other, you don't have to do, some people don't do it that, they just do a Hesse's Law Triangle. They do something like, they do Mg F2 solid, going to Mg F, well, let's do it separate ions, going to Mg2 plus aqueous. Okay, and then the third thing they have down here is magnesium ions in the gaseous state and fluoride ions in the gaseous state. If you think, right, that one there, that's lattice enthalpy, isn't it? Formation. This is the sum of the enthalpies of hydration. And this is delta H sol. And if you're doing this as a Hesse's law, you go against that arrow, so you change the sign with that one, and you go with that arrow, so keep the sign, and that would then let you work out the value of delta H sol. So that's sort of another way of doing it instead of the energy level diagram. Okay, the enthalpy change of solution of magnesium halides show a trend from MgF to MgI. Explain why it's difficult to predict whether the enthalpy becomes more or less exothermic down the group. Okay, now let's have a look at this. Oh, if I just sketch this diagram again, so I'm going to have right, gaseous ions up here. Let's call it X minus, because it could be fluoride or iodide. There's the gaseous ions. We're going to form the, here we're going to form the solid. And here we've got the hydrated ions. Okay. And this is going to be our delta H sol there. Okay, so we need to think about the size of the halide ions. Okay, so F minus is the smallest one. And I minus is the largest. Now, if you've got a small value for if the F minus is small, that is going to give you a larger lattice enthalpy for fluoride ions. Okay, so this is going to be bigger. Right, if that's bigger, that's going to make delta H sol a bit smaller, because the further down that green arrow goes, then the less it's got. Yeah, so that tends to make delta H, the larger lattice enthalpy makes delta H sol smaller, or shall we say less exothermic. Right, so but then let's think about, because the F minus is a lot smaller, let's think about the hydration energy. The hydration energy is bigger, because you've got higher charge density on the fluoride ion than you have on the iodide ion. So the hydration energy is bigger. So that means, well, two steps in the hydration. But first of all, going to the you hydrate in the magnesium. That's the same for both, isn't it? Hydrated that first, and these are still in the gaseous state. So this line here for fluoride is going to be bigger. So that would tend to make the delta H sol more exothermic. So the fluoride ion will give you a larger lattice enthalpy, which makes delta H less exo, but it also gives you a higher hydration energy. That also makes it, that does the exact opposite. That will make it more exothermic. And iodide will do the opposite. So it's hard to predict, you know, which of those two factors is more important. So iodide ions will give you a smaller lattice enthalpy. So the iodide may only go down to there. That tends to make your delta H so more exothermic. But then the iodide ions, they'll only go, they'll only give you less energy out, maybe only go down to there, which tends to make delta H so less exothermic. Okay, question 17. D block elements. Most D block elements are classified as transition elements. Why are scandium and zinc classified as D block but not transition? And you should explain, use full electronic configurations. Okay, so let's start off with scandium, okay, which is there. It's going to have the electronic configuration. Right, we've got 1s2, that's scandium there, 1s2, 2s is full up, 2p is full up, 3s is full up, 3s2, 3p is also filled, and 4s is filled. I'll put that there. Of course, when 3D is slightly lower energy, so that goes there. We've got 1 in 3D. Right. So why is it classified as a D block element? Well, because it's got the last electrons to be filled are in 3D. Right. Why is it not a transition element? Right. Transition elements must form at least one ion with a partly filled D shell. And scandium doesn't do that because the only ion that scandium forms is Sc3+. So the electronic structure there, well, it's going to lose the 4s electrons and the 3D. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. There are no electrons in the D shell. It hasn't got a partly filled D shell. It's not a transition metal. Okay, let's look at zinc now. So I think I'll rub this out. Okay, so zinc, it's the same as scandium. So it's 1s2, 2s2, 2p6, 3s2, 3p6, and then we fill up 4s. And then we have, in zinc, we have 10 electrons in the D shell, so that's 3d10. So it's in the D block because it's got electrons in the D shell. But why isn't it a transition metal? Well, it doesn't form an ion with a partly filled D shell because the only ion zinc forms is the Zn2+ ion. If the Zn2+ ion, you're just going to lose the 4s electrons, they're the highest energy. So you end up with 10 electrons in the 3D shell. So zinc is not a transition metal. Okay, so we've got a compound here, a hydrated chromium compound. They give us the MR and they give us the percentage. Okay, so we're going to have to work out that. And they tell us what the chromium must exist as the 3+ ion there because he forms that species and you dissolve it in water. And then later on we'll talk. So let's work out what is A. Okay, so determine the formula of A and B. Let's work out A first of all. Okay, so we need to do our usual way of give us the percentages and we can work out the Okay, so they tell us, right, chromium is 17.1%, hydrogen 3.94% by mass, oxygen 63.1% by mass, and sulfur 15.83 by mass. Okay, so we now need to these are the masses. So let's work out the moles in 100. So 17.1 grams, yeah, in 100 grams, and so on. So work out the moles. So we've got to divide by the ARs. So chromium we've got to divide by 52, hydrogen by 1, oxygen by 16, and sulfur is 32.1. So we do that, we then end up with 0.32, 0.328, that one there, that's 3.94, that's also 3.94, and that is 0.493. So we're going to divide by the smallest number to simplify that ratio. The smallest number is 3.28, so divide that by itself, you get 1. This one gives you 12, you divide that gives you 12, and that gives you 1.5. Okay, so then to get rid of that 1.5, we're going to have to multiply by 2. So the formula is going to be, we've got 2 chromiums, 24 waters, 24 hydrogen, 24 oxygens, and 3 sulfurs. Okay, so if you want the formula of A, first of all, I would just say that you could just write it simply Cr2H24 O24 S3. Of course, that doesn't really tell us much about the structure of it. So let's just think what it really is. Well, they tell us that what have we got? We have got we tell us that we've got the chrome is in the 3+ state, okay, and we've got 2 of those. They tell us it's hydrated, so all those hydrogens have got to come from water. So that means we must have 24 hydrogens, that's 12 waters. So that means we have got 12 oxygens left over and 3 sulfurs left over. And you can probably see that is almost certainly going to be, those 3 sulfurs and 12 oxygen is going to be 3 sulfate ions. That's what we've got there. And that would be also consistent because look, 3 sulfate ions, that means we'd have a charge of -6 from that. If you look at the chromiums, we've got 2 lots of 3+, so that's +6. So you could get away with writing the formula just as I've written there. I think it's probably safe to say that it is 3.12H2O. That is what A is. That's what we're dealing with, okay? Right, on to the next part of the question then. So the next part of the question then asks us, okay, it tells us that you mix it with water and you get this hexaqua complex, okay, and you mix it with sodium ethane dioate. A ligand substitution reaction takes place, forming a solution containing 3 stereoisomers of complex B. Right, now this is the ethane dioate ligand. What is meant by a bidentate ligand? Well, a bidentate ligand, one ligand forms 2 dated bonds to the central metal atom. And the reason why ethane dioate can do that is because look, you've got a lone pair on that oxygen there and a lone pair there. So each of those oxygens forms a dated bond to the central metal ion. Right, now we've got to determine the formula of B. Okay, write an ionic equation for the ligand substitution and show 3D structures of the 3 stereoisomers of B. So let's do that down here. Okay, so compound A, then we have chromium, those ions there, 3+ ions. Right, and then we're going to react that with 3 ethane dioate ions. We've got 3 of them. We only need 3 of them because they're bidentate. Each one is going to form 2 dated bonds. So that's 6 dated bonds in total to the chromium. So what's going to happen there is we are going to push all those waters out and replace them with 3 of those ligands. So that's C2O4. Now what's the charge on this going to be? Right, it's going to be -6 on the ethane dioate ions. You've got 3, 2 minus each. You've got +3 on the chromium, so that's going to be 3 minus there. And we're going to have our 6 water ligands pushed out. Now it asks us, oh sorry, a mistake there. We don't replace all of the waters there. That's we replaced all of them. The question says we only replaced 2, so I'm going to write down the right version there. Sorry about that. Okay, so we're only going to replace 2 of those. So we're going to have CR. We've still got 2 waters, and we've got 2 of those. That means there's just going to be a 1 minus charge on that, and we're only going to get 4 waters there. So that's the correct equation. That's not correct, that one there. So that's what we replaced. If we replaced all the waters, it says we only replaced 2 of them. Now it says you can get 3 possible stereoisomers there. Let's see how that is possible. This exists as 3 stereoisomers. So let's see what kind of isomerism is going there. We know there's a chance of cis-trans isomerism, EZ if you like, and there's also a chance of optical isomerism. Remember, when you have bidentate ligands, there's a chance of optical isomerism. Right, let's draw our chromium here. We've got 2 ligands going back into the plane of the paper, 2 coming out, there's wedges, and we've got 1 up and 1 down. So we've got an octahedral arrangement of the 6 bonds there. Okay, so let's see what could happen there. Well, we could have a possibility where we've got the 2 water ligands which are opposite each other. And here we have got the I'm going to draw this ligand just as, well, it's complicated. I'm going to draw the ethane dioate ligand as that with an oxygen, just a line. Okay, so we can have, that's one of the bidentate ligands there, and the other bidentate ligand would go there. So that's one possibility. What else could we have? Well, we could have a situation where the waters aren't opposite each other. There's 1 up and 1 down, going back into the plane of the board paper, out of the paper. Okay, so let's have the 2 waters, instead of being opposite, let's have them next to each other. I could choose any 2, but I'm going to choose those 2. Okay, and let's draw where the bidentate ligands would have to go. You have to have 1 there, 1 there, 1 there, and 1 there. And of course, you probably remember that that can have an optical isomer now. Okay, so if I draw a mirror image of that, so here's our mirror, and I'll draw chromium here. Right, 2 into the plane of the paper, 2 coming out of the paper. Right, the mirror image of that, so that means you have the waters over on this side now. This one, this bidentate ligand there is going to be reflected there, like that, and this one like that. Now, those 2 I've drawn there, these 2 things, these are non-superimposable mirror images of each other. They are optical isomers. And you also have this other possibility here. This can't exist as 2 optical isomers. This is just a third one you can form with the water molecules opposite each other. They're the 3 species, the 3 different isomers you can form then. I'm going to leave that paper there now and continue it in the next video.